What question am I reluctant to ask here? Like, in this example over here, if I was to say, okay, now find y of t, right? I'd be like, oh, okay, no problem. V is equal to dy dt, right? I integrate. I get y of t is equal to y naught plus v naught times t minus t naught minus 1 half g t minus t naught quantity squared. I mean, I'm going to skip the details here, but you can derive that through simple integration. So if I wanted to find, I guess we could do it. I don't know. I mean, yeah, you can do it. Fine. Can you find y as a function of time here? Or rather, x as a function of time? I guess we can do it. It's not too bad, is it? What would we have to solve? We'd have dx dt equals to what? Plus or minus 1 over the square root 2 beta t over m minus 2c, right? So you just have to integrate both sides to find x, right? So x is equal to the integral of plus or minus dt over the square root of 2 beta t over m minus 2c, right? So we can solve this integral. Actually, it's not too bad. Just make that equal to w, right? And so this is like plus or minus m over 2 beta dw over the square root of w. Because dw is 2 beta over 2 beta dt over m. So that means dt is m over 2 beta dw. Just make a w substitution. What's the integral of the square root? I'll bring the 2 downstairs. That's nice. So this is just plus or minus m over beta square root of w plus some constant, which I better not call c tilde. And so there you have it. C tilde plus or minus m over beta square root of 2 beta t over m minus 2c. There's the position as a function of time if we have a cubic dependence of the friction force. Every once in a while I will say something like, we need differential equations to treat friction. This is what I'm talking about. Yes, sir? Here to here? Or here to? Yep. Oh, so if w is equal to what's inside the square root, yep, then dw is what? So solve for dt. And that is precisely what I did here. So that's just, yeah. Man, you guys are so quiet in here. Making me nervous. All right. So we can work more of these tomorrow, of course. But what I want to do with the remaining time is show you the technique of the next section. All right. So the next section concerns. Oh man. All right. So the next problem, which is section, what are we? Section 9 point. I lost track. 3? Is it 3? I think section 9.3 is on how to solve a y prime prime plus by prime plus cy equals to 0. Right. How do you solve a problem like that? So here's what you do. Let y equals to e to, let's say, the lambda. Do you guys want y prime prime? We'll make it y prime here. This is in slightly ambiguous notation. So let me just tell you y prime is a notation for dy dx. We're going to use x as the independent variable. Okay? I've shown you some examples where we use t as the independent variable, right? Like, well, this one used x as the independent variable. This one used t as the independent variable, right? X independent variable, t independent variable. I mean, we kind of go back and forth. So let y equal e to the lambda x. What's y prime equal to? It's lambda e to the lambda x, right? I mean, we multiply by the, I'm assuming lambda is a constant. And then what's, yeah, it looks like it too. Y prime prime is what? By the way, guys, don't be like me. Write your lambdas correctly. They're supposed to be that. You guys see the difference? By the time I noticed, it was already ingrained. I write my lambdas backwards. Sorry about that. But yeah. So this is what? This is lambda squared e to the lambda x. So if y equals to e to the lambda x is a solution to a y prime prime plus by prime plus cy equals to 0, let's call this thing star, then it is necessary that what? A lambda squared e to the lambda x plus b lambda e to the lambda x plus c e to the lambda x be 0. Just differentiating my proposed solution. Okay, so the two methods I've showed you up to before this point, all right, integrating factor technique and also the separation of variables technique, they still have the feeling of derivation. Like you're doing a series of steps to get to the answer, right? Here I'm showing you something rather different. I'm showing you this idea that we guess a general template, a general form that might be possible for the solution. Then we're plugging it into the differential equation and seeing what works. So the thought process here is a little bit different, right? It's a little bit more clever, really. Good news, what's clever is usually easier. So what happens here? What can you do to this equation? Right. Now, is that ever 0? No, it's not. Even if, well, okay, it's just never 0. So that's a lambda squared plus b lambda plus c equals to 0. This is the so-called characteristic equation of star. Its solutions characterize, in fact, the solutions of star. What should we expect, by the way? Let's just look at an example. This is kind of almost too simple an example. Well, actually, it's a complex. Let me do something more less weird. All right, so y prime prime plus 3y prime plus 2y equals to 0. Let's find solutions to this. So what we do is, okay, following our general scheme here, this gives me lambda squared plus 3 lambda plus 2 equals to 0, which can be rewritten as lambda plus 2 times lambda plus 1 equals to 0, right? So what does that tell me? So my first solution may be y1 is e to the minus 2x, and y2 is e to the minus x. Those in fact will be solutions to the given differential equation. And it's fun. I mean, you can go back, if you don't believe me, check it. Is it true? Plug in e to the minus x up here. What do you get? Y prime prime. Minus e to the minus x plus e to the, so you do two derivatives, you get back to e to the minus x again, right? And then you get what? 3 times the derivative of e to the minus x, which is what? Minus 3e to the minus x. So I get plus 1 minus 3 plus 2 again, 0. That's not an accident. If you plug in e to the minus 2x, this produces a 4. That produces minus 6 plus 2. 4 minus 6 plus 2, 0. Not an accident. Those are solutions. What's the general solution look like? Well, here's a little theorem. If y1 and y2 solve ay prime prime plus by prime plus cy equals to 0, then y is equal to c1y1 plus c2y2 is also a solution to this. Proof. So what does it mean to say that they're solutions? Assume y1 and y2 are solutions. We get what? We get a y1 prime prime plus b y1 prime plus c y1 equal to 0, and we get a y2 prime prime plus b y2 prime plus c y2 equals to 0. So then it's pretty simple. Multiply the first equation by c1, we get a times c1 y1 prime prime plus b times cy1 plus c times c1y equals to 0. How do I know I can pull the constant inside the second derivative? Is that a property of second derivatives? Can you pull constants inside them? You can definitely pull constants inside first derivatives, right? And a second derivative is just two first derivatives done one after the other. So you pull the constant in the first and pull it in the second just by iterating. Yes, we can pull constants inside second derivatives, not a big deal. There's a prime missing here. And likewise for the second one, right? And then you just take these equations, right? Add them, and what do you get? You get a times, and using properties of the derivative, right? I can use a sum of derivatives as derivative of the sums, and that's also true for second derivatives. But what is that? That is exactly what you need to prove. That's what I'm trying to prove. I'm trying to prove that this linear combination c1y1 plus c2y2, this thing right here, right, is a solution. This is what's needed. I take the second derivative of it, multiply by a, take the first derivative, multiply by b, take itself and multiply by c, add them together, and you get 0. That's what it takes for it to be a solution. Yeah?
In the second equation, c2y1
Oh, yeah, that was definitely supposed to be a 2. Sorry about that. Right. All right. Sorry, this is a lot of writing, but not too much thinking, this theorem. So we can use this theorem in my example above. What do we get then? By the theorem, we have y is equal to c1 e to the minus 2x plus c2 e to the minus x is solution. In fact, that's the general solution to that differential equation. Well, I'll have to tell you the rest tomorrow. Thanks, guys.